Okay, so hello everyone, and thanks for coming to my talk on understanding the Ruby Global VM Lock, or JVL, by observing it. So, who am I to be speaking to you about this? My name is Anjo, and I am a senior engineer at Datadog. I've been a big Ruby fan since I started using it around 2014, and I really enjoy exploring language runtimes such as the Ruby VM or the Java VM and others. I'm also a big fan of application performance. I really like the idea of making the best out of the hardware that we paid for and getting the most out of it. I also really enjoy making visualization tools to uncover new insights, and by looking at our applications in different ways, understanding them even better. I'm currently working on building Datadog's open source continuous profiler for Ruby, which is shipped as part of the DD Trace Jam. So this thing. If you're interested about it, come talk to me about afterwards. And I also thank my employer, Datadog, for sponsoring this trip. So I'm here today to talk about the global VM lock. What it is, what it is not, how can we observe it, how can we measure it, and what should we take away from all of this information. So let's get started. Around 2014, I started using Ruby at my first job. So I wanted to know more, go deeper, kind of become a master of this tool that I was going to use on my day-to-day job. At some point, I saw some references online about this JVL thing, or maybe it was the GIL. And then, sometime later, someone told me, oh, that's the JVL is why Ruby doesn't run on multiple cores. And I went a bit like, OK, I guess that's fine. I think I understand it. But actually, it really took me a long time to get to terms to understand what's the impact of the JVL on application performance, especially on application latency. It also took the work of Jean Boussier and Matt Valentine-House at Shopify to make the JVL much easier to observe. So thanks Jean and Matt for this work. So all of this has led me to create the JVL Tracing Jam, which produces this visual timeline of what the Ruby Global VM Lock is doing so that we can kind of learn more about it. And I got retweeted by Matt, which was pretty cool, and I was pretty excited. So I did this talk so I could share what I learned so far in my saga. So let's start by asking, what is the Global VM Lock, or JVL? So when we run our Ruby applications, often we call Ruby some script. And we often don't think about the Ruby part. We're just thinking about our application, what we're trying to do. But looking at the Ruby part, Ruby is actually a VM, and it's a big problem that is written mostly in C with a bit of Rust and a bit of Ruby. So you might hear this Ruby VM also being called C Ruby or MRI. So this is where the global VM lock acts. So when we're writing some Ruby code, we might start a couple of threads. In this example, we start 2 threads. One prints hello, the other prints world. And maybe when we're not creating the threads directly, so maybe we're using a threaded web server such as Puma, or using a background job processor, whenever threads get created in a Ruby application, they actually get mapped one-to-one to operating system threads. So often they don't get shown by default, but if you go on your OS task manager and search for the option, somewhere in there will be an option to see threads. And if you select that option, you will see that for every thread that you have on your Ruby application, there is one thread in the operating system. So they get mapped one-to-one. And this is important, because it means that this Ruby app that we know is a big problem that is written in C, it's also a program that uses multiple OS threads, or it's a multi-threaded program. And this means that the global VM lock is actually a mechanism, or a strategy, if you will, to ensure correctness of Ruby, the multi-threaded C program. So this is a kind of a big definition to unpack. So I'll talk more about it. But at a high level, you need to think about the global VM lock as just a mechanism inside the VM to ensure correctness. So as a quick aside, if you've never used locks, you don't remember I heard about a lock, but I don't quite remember what it is. The idea of a lock is that it's a mechanism that allows only one thread, the thread that is holding the lock, to work at the time. So if you think about, for instance, a swing, only one person can be on a swing at the time, and then the other people that want to go on the swing, they need to wait. If you try to put multiple people on a swing, maybe you can, but things will go badly. Or you can think of it as a pen. If you have multiple people and only a single pen, only one person can be holding the pen and writing, and the others need to wait. So a lock is a bit like this, but for computers. So when a thread inside the Ruby VM is running Ruby code or interacting with Ruby VM data, it needs to be holding the global VM lock. This is the rule how the mechanism works. It also means that no other thread can be doing the same, and that the other threads need to wait for their turn to be able to execute. So you might have also heard, like as another aside, about the global interpreter lock. What is the global interpreter lock, or GIL? Very easily, it's just what Python calls their JVL. So Python is also very widely used, and a lot of people have, their first language is Python. So often it's easy to say, oh, Ruby also has the GIL, and people kind of automatically know, oh, I know what the GIL is. So, but it's, in Ruby it's called, internally it's called the JVL, but it's the same concept. And actually this concept, or this mechanism, it happens in multiple places. So actually, old versions of Linux actually had the big kernel lock, or BKL, which was exactly the same idea, but inside the operating system. So it comes up and again and again. As another aside, maybe it's not called global VM lock, maybe it's the great valuable lock. So last year, Koichi opened a PR, and he mentioned that the JVL is no longer process global. So he proposed and changed the names of a lot of these concepts inside Ruby. And Koichi went on to say there are functions that still include JVL in the name, and he didn't have a good name to replace them. So maybe he proposed, maybe JVL stands for Great Valuable Lock, or something like that. So the idea is that this JVL was renamed in Ruby 3.2, but it's still kind of the same concept. It just got a new name. And this concept also applies to older Ruby releases. So we've talked about what is the JVL. So let me also mention a bit what is not the JVL. So I'm sorry. OK, so the JVL allows concurrency, which is the illusion of working on multiple things at the same time by switching between them. So for instance, if we have our Ninja can be writing some code, or standing around, or planning. And if our Ninja kind of switches between tasks fast enough, it actually seems like 3 ninjas, but it's the one red ninja. It's just doing one thing at a time. This is in contrast with parallelism, which is when you actually work on multiple things at the same time, which is when you have multiple ninjas, and then you can be working on multiple things at the same time. So this is a difference, the JVL allows concurrency, but not parallelism. Furthermore, if you think about it, if you've been around for a while, this is a bit like a 90s single-core PC. The PC could only do one thing at once, but it just switched around, so it looked like you were running 10 applications at the same time. And in this case, the image credit goes to me, because I'm a huge hoarder of old PC hardware. So if you're ever curious, come talk to me about this. I don't know why would you, but yes. So the one question I would like to touch upon is, if the JVL exists, then why do we really need concurrency APIs? I thought the JVL kind of prevented these issues in Ruby. And the thing is that Ruby has mutexes, condition variables, queues, sized queues. There's the concurrent Ruby gem, which provides a lot of concurrency utilities and other things. And the key thing to think about here is that the JVL only protects the Ruby VM data or state. It really doesn't protect your application. So when you don't use the concurrency APIs and you use multiple threads and fibers and concurrent things, you might not end up with the results that you wanted. So as a simple example, here's this simple piece of code where I start from is set to 100,000, 2 is set to 0, and then I have a simple loop that just takes 1 from, and then puts it into 2. And then at the end, it's supposed to give 100,000 in 2, and from will be set to 0. But actually, when I run it on my machine, one of the times I got this result. So I got 11 more than what I got going in. And the problem is, this is a good example, because Actually, the solution is that this is a valid result for Ruby. The global VM lock protected the Ruby VM state, but it's actually not what we wanted in terms of our code, our application. And to fix this, this is where we need the concurrency API. So a mutex is kind of basically a lock in Ruby, and so I've added the lock there. And by changing our example with the lock, now if we rerun it, we get the right result. So this is the difference between the JVL protecting the Ruby VM state and the JVL not really protecting our application, and our application needs to use concurrency APIs. So key insight number one is that the JVL does not protect Ruby code running in multiple threads. It only protects the Ruby VM. But there's an asterisk there, which is that except sometimes the JVL actually kind of protects your code, but it's often by an accident or an implementation detail, and you shouldn't rely on this because this changes between Ruby releases or might even look correct, but maybe if you add enough threads, it will break. So you should use the concurrency tools if you need to, and you shouldn't rely on the global VM lock because it might break between releases. So as another aside, if you ever use like JRuby or Truffle Ruby, there are alternative high-performance Ruby implementations that actually don't use a JVL. They use other mechanisms to protect their own VM data, which actually means that they get concurrency and parallelism. So it's like an interesting contrast with the regular CRuby VM. Okay, so we've talked about what is the JVL, what is the JVL not. Let's talk about the interesting part, which is observing it. How can we observe the global VM lock or JVL? So in Ruby 3.2, there was a new API introduced called the JVL Instrumentation API. And this API is at the C level only. So the idea is that whenever threads in your Ruby application are about to get the JVL or release it, basically Ruby will, like you can add some callbacks and Ruby will call them, and so you will be able to learn about these events. So this is only available for native level extensions, and so because I wanted to look at this information, I built my own gem, which is the JVL tracing gem. The JVL tracing gem takes this information and draws it, the JVL usage in a visual timeline, such as the one shown there. So if you want to use the JVL tracing gem, it's 3 simple steps. Step number 1 is you add it to your gem file as usual. An important detail is that because the new API was only added on Ruby 3.2, you really need Ruby 3.2 and above to actually use it. Sorry. Maybe someday, sometime, someone will figure out how to make it work on all the Ruby versions. Step 2 is you start it, you give it like the name of the output file, you run some code, and then you stop it, and then you get a nice like JSON file that you can upload on the ui.perfetto.dev website. So this is pretty simple, and you get like this visualization, and Perfetto is a tool that Google built for visualization of this kind of performance data, so I'm just piggybacking on it. So I'll show a bunch of like links and examples ahead, and if you want to play with them live, I'll also show the link at the end. You'll be able to like click around, go and play with Perfetto yourself. So yeah, if you're interested, I would recommend doing that. So let's look at what it is about observing the JVL. So the tool provides like a line for each thread, and then time flows from left to right. So we can see what the state of the JVL was along these multiple threads. So basically we show different states, and the states are not exactly the ones that the Ruby VM uses internally. We've kind of renamed a few to make it a bit more clear, but some of the states are started tracing, started and died, and they are all referencing like starting and stopping of threads, so that should be kind of very easy. And then there's waiting, and this state is when a thread is waiting for more work, or it's waiting, it did a network request and it's waiting for a reply from the other system, or a database request, or it's just doing some sleep, so this is waiting. There's also a state which is running, which is in blue. So this is when a thread is actually making progress. Things are happening. It's going ahead. And then there's one of the most important states to keep in mind, which is the once JVL state. The once JVL state is when a thread, like, it's all ready to go, but it's kind of, it needs to wait for the JVL. So it has no pen. It needs to wait. So it's like, can I go? Can I go? And it can't. It's waiting to be able to execute. And finally, there's also a state to represent garbage collection. So let's look at an example. Here's a very simple method, counter loop, that just counts, basically very simple, counts to 1 billion. And then I start 2 threads in this example that are both running this code. And if we look at it, well, we see the 2 threads. We see concurrency, but not parallelism. So we see that threads take turns to execute. So when one thread is running in blue, the other thread is wanting the JVL, and then they kind of go back and forth. So we see this like alternation of this one thread runs, the other runs, one runs, then the other runs. And then when multiple threads want to work, we kind of see that Ruby is switching them between them every 100 milliseconds. So the scale at the top is every 100 milliseconds. So we're seeing how Ruby is kind of going back and forth between both threads. So if we extend this example from 2 threads to 10 threads, we start observing kind of like a very interesting pattern, which is like threads spend very little time executing, so the blue part is very, very small, and then they spend most of the time waiting to be able to execute again. So they could be executing, but they can't because they're waiting for their turn. And you see that Ruby kind of goes like in turn and gives each thread 100 milliseconds and then comes back and gives each thread 100 milliseconds again. This means that as you add more threads to a Ruby app, you can impact latency if all of the threads are fighting for the JVL. And if you look at the previous example, but just slice it to one thread, you can actually see the story of the one thread being really, really impacted in terms of latency, because this thread is running for 100 milliseconds, then it needs to wait for 900 milliseconds, where it's just it could be running, but it doesn't have the JVL, so it needs to wait around, and then it can run again, and so on and so forth. Of course, Ruby web apps are usually not like this, so I'll show a few more examples with web apps, because usually web apps do a lot more network calls and this kind of I/O, and not as much processing. So this is not supposed to be a very realistic example, but it just kind of shows the very, very worst case, which is when you have many threads and they are all competing for the JVL at the same time. So another key insight is that if you're using threads, your app latency does not depend only on each request or method's performance, because even highly optimized Ruby code may take longer if it needs to wait for the JVL. So this is a pretty important point. You might have optimized this one controller, this one request, this one piece of code. It's beautifully optimized. You spent a bunch of time profiling it, etc. And it might be impacted because something else is happening at the same time. So let me repeat that, because I think this is one of the most important points. A specific web request may be slow, not because of what that request is doing at all, but because there's another request or another thread that was doing a lot of work at the same time. So this might be a bit surprising that suddenly, it's not just the code that you're seeing, it's also some other code that may be running off in the corner. And yeah, if you've ever heard of the concept of noisy neighbors, Ruby threads have this issue of they're kind of noisy neighbors in a way. So another example. So if you have 2 threads, but then one thread kind of finishes its work, like the thread on the bottom, and then Ruby doesn't have to switch the JVL. So the top thread still has work to do, so it will keep on working, because now there are no more threads wanting the JVL as well, so it will work for a long time. So that should kind of match what we expected. Another example is, okay, what if we are doing network calls? And in this example, we have 2 threads. The top thread is doing a bunch of network calls, and the bottom thread is actually not created by me. It's the Ruby timeout. And the Ruby standard library timeout is actually implemented as a separate thread, so that's the bottom one that you see there. So the only one I wrote is the top one, and you see that the top one spends some time running, then waiting. And this waiting is, it's waiting for the network. Then runs again, then waits, then runs again, then waits. So this is kind of what you expect on an app that is doing a bit of CPU work and then a lot of network connections as well. And this means that obviously other threads can run on the meanwhile. So for instance, you see there are periods, for instance, in the middle you have a period where both threads are waiting. And this is fine. no thread wants the JVL, so no thread has the JVL. Ruby is just, OK, I have nothing to do. OK, so far, we've seen that threads each get 100 milliseconds, and that seems kind of fair. Like one gets 100 milliseconds, the other gets 100 milliseconds. Are there situations where Ruby is unfair, is the question I want to ask. If we go back to the network call example, and I'll even show the code, it's kind of weird, but I'm basically running like in a loop just a request to get the Google front page. And if I do like this very tiny example and I run it on my home network connection, I got 17 requests per second. So in a second, I can get the Google front page 17 times. That's OK. I guess my network connection could be a bit better, but it works. So if we take this example, and we see that there's a lot of waiting. So most of the time is spent waiting. And if you look really closely, you'll see like very fine lines of blue there. It's because like the period spent running is actually like almost nothing. This application is truly dependent on the network to make progress. So if we add the counter thread, if we take this and we add the counter threads that I added in the beginning, what would you expect to happen? You might expect that, OK, one thread is mostly doing network, and the other thread is mostly doing CPU. So it's fine. It should be fine. And actually, it's not. So when I run this, in 1.5 seconds, I was able to do 2 requests to get the full Google front page. And this is a very important detail and actually quite surprising. And we can use the JVL tracing gem to explain what happened here. So before, we had a lot of waiting. And afterwards, how it looks is like this. So the top thread that had a lot of waiting became that top thread in the second example, which is spending most of its time wanting the JVL. And then we have the bottom thread, which is the one running the counter. So we need to really zoom in on Perfetto to see what's happened. But what happened is that the top thread runs for a bit. Then it waits for the network, but then Google, we get an answer. But the problem is, by the time we get an answer, the other thread has started working, and so we need to wait 100 milliseconds until the first thread runs again, and then the first thread runs again for a bit, and then waits again, and then it needs to wait for a long time. So basically, the second thread always gets 100 milliseconds, and the first thread runs for a tiny bit, and then it needs to wait for the network, so it immediately gives up the JVL and is impacted by the latency. So this is the kind of thing that might not be obvious if you're not kind of looking out and looking at how the JVL is being impacted in your application. So key insight number 4 is that the global VM lock is not always fair. So Ruby threads, if you use Ruby threads and fibers, you get more utilization and you get more throughput out of your machine, but you have the potential to penalize latency. So it's a trade-off. Ruby, as a reminder, the rules for Ruby kind of switching, giving the JVL to another thread is that Ruby will give each thread 100 milliseconds to run if it keeps running without giving up the JVL. When a thread blocks, doing like reading a file or going to the network or a database, locks or sleeping or something like that, the Ruby will switch the JVL from one thread to another. Or at certain points, when inside the VM or the C extensions, Ruby also kind of releases or acquires the JVL. So furthermore, you might remember that Rectors were introduced in Ruby 3 as a new concurrency primitive. And Rectors are supposed to provide parallelism, and you're supposed to communicate between Rectors with messages. So the question is, what happens if we modify some of our examples to use Rectors? How will they fare? So example number 7 is that if we take the network plus counters example, then and we put each thread on a separate Rector, then it works perfectly. So we now see that the top thread spends most of its time waiting on the network, and the bottom thread spends most of its time running. This is why the JVL got renamed in Ruby 3.2, because each Rector gets their own JVL, so the global part is not really true anymore, and this is why it was decided to rename it. And because different Rectors have different JVLs, both of them can run at the same time, and so parallelism and works beautifully. As well as the many counters example that I've shown you in the beginning. Now you see like a sea of blue, because if every thread is in a separate Rector, they can all run at the same time. So Cool, we've proven that indeed rectors are parallel. So one other thing I wanted to mention is the JVL tools gem. So the JVL tools gem was built by Shopify, and it also hooks on the same JVL instrumentation API as the JVL tracing gem, but it exports this information as metrics that you can then push somewhere, alarm on it, have graphs, have dashboards, all of that. So the gem provides data such as like how much time like your thread spent waiting for the JVL, so you can see like, oh yeah, I was impacted, my latency was impacted during this period, or you can even like get a count of how many threads are waiting for the JVL at the time. So you see like, if you start seeing lots of threads waiting, then that means latency is about to be impacted a lot. So check out this gem, is also very interesting in like looking at this data in another way. So takeaways, like what should you do with the information that I shared today? So the first thing is like you should keep using threads and fibers in most cases. So I'm not trying to scare you into not using them. They worked so far for most of your applications, like they will continue on working, it's fine. The thing is, like, you should avoid using too many threads if you are latency sensitive. So for instance, if you have a web app and you have like a 4 vCPU machine with 8 GB of memory, an example starting point you could start from by Nate Berkopek, one of the maintainers of Puma, is, okay, start with 4 workers, 5 threads, and then work from there. So this is a rule of thumb, but you should kind of figure out what's the correct number for your specific setup. So you should separate latency-sensitive code from other things. So for instance, if you have a bunch of endpoints that are serving really important user traffic, and then you have one endpoint, which is the admin endpoint that generates a huge CSV and exports it something, you should probably separate that out, maybe as like a background process on Sidekick or something like that, just to make sure that they don't impact each other. Remember that the performance of a Ruby web app endpoint impacts other endpoints in the same app. So also, my recommendation is don't guess, experiment and measure. So tools such as like profiling or benchmarking in production are really important. And it's like, at least you should have a realistic setup, if not in production, because as you kind of saw, like if you look at something in isolation, you might not have this effect of like multiple things fighting for the JVL. So you need to have like a realistic production setup to really be able to measure these things. You can use the JVL tools gem to measure and alarm and graph the impact of the JVL on your application, and you can use the JVL tracing gem to observe what's going on. You can also like try Puma or another web server, such as Unicorn or Falcon, in a 1 thread per process setup and see how that behaves. Are your latencies basically unchanged? Or do you see big change in latencies? This could be like a really good indicator if you are how much you're being affected or not by the contention in the JVL. So furthermore, like Rectors, JRuby, and Truffle Ruby can unlock both performance as well as latency benefits. And I wanted to call this out because often we kind of say in the community, oh, JRuby is faster and Truffle Ruby is faster, but then it has a few challenges. But it's not just faster in running single-threaded code, but like this latency benefit of they're not using the JVL is also quite relevant. And Rectors can also provide some of this. And always remember that the JVL is not meant to protect your code, even though sometimes it kind of does. To finish off, I wanted to say that like the future is bright. So Ruby is always improving and evolving. Recently, we got Rectors. We got YJIT from Shopify. We got the Many project that Koichi spoke about last year, where he's thinking of undoing the mapping where one Ruby thread matches one OS thread. So maybe let's change that. We also there was also some discussions on Twitter when I blogged about the JVL tracing gem about maybe considering doing the thread switch like to lowering to 10 milliseconds instead of 100. So the takeaway I would like you to go from here is like you should measure and you should experiment on your app. You should not take any of this, like I've given you the tools, you should not take this as like written in stone because Ruby is always changing, Ruby is always evolving, Ruby is always going to get better. So thank you. That was my talk. You can find my email there. You can also find me on Twitter. That's the link if you want to play with Perfetto. You don't even have to run anything on your machine. You can just go on there and click the Perfetto links, and then you can browse it. And I would like also to thank my employer, Datadog. And yeah, come talk to me if you're interested about any of this. And thank you.